I am Dr. Rajiv Mishra from IIT Patna. The topic of this lecture is hot data analytics for real time streaming in IoT platform. In this lecture, we will discuss real time data processing in IoT edge platforms with Spark streaming and sliding window analytics. We will also discuss the case studies based on a particular use case, that is with Twitter sentiment analysis using the streaming. Let us give you a IoT platform an overview which we have already covered. So, it is a recap that this particular IoT platform is divided into the things, that is then coming the cloud IoT platform, and after that this edge or IoT edge is being added. So, therefore, these sensors and actuators are part of these things, and when they will ingest the data, it goes into the cloud through the edge. So, the connectors which are there for data ingestion. So, data ingestion will happen using the Kafka connector or MQTT streams. This particular data stream is put into the system, that is the cloud IoT platform. Now then, you know that this is the routine that is called real time data processing. If it is the hot path data analysis, it will be performed using the stream analytics, which we are now covering up. So, for this there will be the tools which are called Kafka, which we have covered. So, this will ingest the data for and enabling this real time data processing. So, we are going to cover for this part which will be performed in the cloud, that is using the Spark streaming. This data analysis will give the insight, and this in turn further be used by business intelligence for the action part. So, therefore, finally, the end use is with the consumers who will be the beneficiary for making all the decisions which is taken by. So, therefore, there are three types of data flow which we will cover here. The first one is called hot path data analysis. So, data streams as it comes, it will put in the real time data processing using Spark streaming, which we will cover. Besides this hot path, let me tell you about that we are also having two more type of data analysis, that is called cold path, that is a form of batch processing. When you say batch processing, that means data will be put at the rest in one of these database technologies, and then using this particular data at a later point of time will be performing various kind of insights and business intelligence called cold path. Warm path is to do the small batch processing in the batches of a small part will be taken up for this particular analysis, comes in between the hot path and the cold path analysis. So, the topic which is kept here in this lecture is dealing with the hot path analysis. So, data is routed to three different paths. One is called hot path or cold path or a warm path. So, hot path data is the data that is processed as it is ingested into the system, that is the stream analysis is to be done for hot path data, and that is to be done in the real time. So, as it gets processed within the seconds of its happening, so when the message hits the hot path, it is processed and it is presented to something in the consumption layer. So, consumption layer will consume that processed information, and this is called the hot path. The output of the hot path to the cold storage system, or let us say that storage system to make it persistent, and is consumed by these APIs. So, the data which is written in the real time, but APIs might be querying that particular data that was written an hour ago in the batch mode for this hot path analysis. So, the main thing about the hot path is that when you are processing the data in the real time, it is happening. However, when it is consuming, that might be querying old data that was processed an hour ago. So, that means the processing is to be done in the real time, and that result will be displayed into the dashboard, that is the insight will be available and will be given to the consumption layer. So, let us discuss about the traditional stream processing, and then we will go and discuss more advanced versions. So, streaming data, you know, that is received from various data sources such as live log and system telemetry data, IoT device data. So, these streaming data now is ingested using some of these tools which we have already covered, that is Apache Kafka or Amazon Kinesis. So, this particular streaming, so that is ingested into the system and is then processed in parallel on the cluster. So, you can see that this particular source will give the continuous stream of data into the system, which is then put in the process under this platform which is called a cluster. So, the results are given to the downstream systems like HBase or Cassandra, and so here you can see that the results are now put in the database like HBase, Cassandra and Kafka, etc. So, now there are set of worker nodes, each of which runs one or more continuous operations, that is what is shown. So, each continuous operator processes the streaming data one record at a time and forwards the record to the other operators in the pipeline, that is the sync operator. So, data is received from that ingestion system via the source operators and given as the output to the downstream systems via this sync operators. So, continuous operators are simple and natural model. However, this traditional architecture also has met challenges with today's trend towards larger scale and more complex real time analytics. So, therefore, this traditional stream processing which we have covered in the previous slide has the following limitations. First is that it is having the fast failure and straggler recovery. So, in the real time system must be able to fastly and automatically recover from the failure and stragglers to provide the result, which is challenging in the traditional system due to the static allocation of continuous operators to the worker nodes. So, due to these issues, this is the limitation of traditional stream processing. The other limitation is in the form of load balancing. So, in a continuous operator system, uneven allocation of the processing load between the worker can cause the bottlenecks, and the system need to be able to dynamically adapt to the resource allocation based on the workload. So, therefore, load balancing is again another limitation of traditional stream processing system. Third one is unification of streaming, batch and interactive workloads. So, in many cases it is also attractive to query the streaming data interactively or to combine it with the static data set in most of the application, that is called pre-computed model, but this is hard in continuous operator system which does not designed to the new operator for ad hoc queries. So, this requires a single engine that can combine both batch streaming and interactive queries, and that is unification of streaming, batch and interactive workload is again a limitation of traditional systems. Then the fourth one is advanced analytics with the machine learning and SQL queries. So, complex workloads requires continuous learning and updating data models or even querying the streaming data using SQL queries. However, in the common abstraction across these analytics makes the developer job much easier. So, let us take the example of the streaming data processing. So, let us say that the bank transactions are continuously flowing and coming in the form of the streams, and this particular stream data need to be processed as the data is entered into the system, that is called hot path analysis. Now similarly, the sensor data. Now sensor data also comes in the form of a data streams. So this streaming data need to be analyzed to find out the anomalies which is arising in this particular sensor data. So anomalies is the deviation from the specified state of the system. So this particular anomaly is to be detected in the streaming data in the real time. Similarly, the tweet data is also coming in the streams. So tweet data is also come in the streams, need to be analyzed as it is ingested into the system. Now the question is how to process this streaming data. Now this processing of the streaming data requires to be completed within a particular time window before the next batch of the streams arrives in the system. So therefore this particular processing which is in the real time needs to scale even to the hundreds of the nodes, so that in parallel they will be able to complete the execution of the streaming data. Otherwise the application may miss the insights which is there inside that streaming data which is ingested into the system. Similarly, this is one aspect called scale to hundreds of the nodes. Second is that it achieves a low latency. Low latency means that this particular processing of the streaming data has to be completed very fast. So it has to achieve the low latency, otherwise it may miss the batch and a new batch of the data will come and the previous batch will remain unprocessed. Third one is to efficiently recover from the failures. So failures in the sense, if the nodes are down, even then the system has to work irrespective of the node failures. So therefore redundancy and all that are becoming a norm, and you know that in a big data system the number of clusters where the nodes are maybe considered as a commodity nodes, they may fail. So the system has to ensure that it will efficiently recover from the failures. Fourth important thing is the requirement that sometimes it has to be integrated with the batch and the interactive processing. So your stream analytics or analysis has to be integrated also with the batch and interactive processing for better insights sometimes. So all these four requirements is bringing up or is making the specification for streaming data analytics, and you can see that as you have seen the first requirement that it has to be scalable. Therefore the streaming processing system, it has to be a distributed processing system where it can be scaled to hundreds of the nodes depending upon the pace in which the data is coming. So this will have something called a fast data processing. So fast data processing requires the scales to the hundreds of the nodes here in this case. Now what people have been doing so far, let us see how this particular four requirements will be able to solve. Let us people use it, they build two different stacks, one for the batch and one for the streaming, often both process the same data. So existing framework cannot do both, because either the stream processing of hundreds of megabytes with a low latency or the batch processing of terabytes of the data with a high latency, both cannot exist in the system. So it is extremely painful to maintain two different stacks and different programming models, doubles the implementation cost. So much issues are there in this mode of combining batch and stream with the two different stacks. Therefore next issue is the fault tolerant stream processing, how that is being done in the traditional processing models. So there is a pipeline of nodes and each node maintains a mutable states, and each state records the updates the state and a new records are being sent out. So now maintaining the states in this fault tolerant stream processing in a traditional mode where the mutable states is lost if the node is failed, making this stateful stream processing fault tolerant quite challenging in this particular case. Now let us understand about the data streaming. So data streaming is a technique for transferring the data so that it can be processed as a steady and continuous stream. So example is that streaming technologies are becoming increasingly important with the growth of the internet. So here you can see that the streaming sources such as the YouTube, Netflix, Twitter will give a live stream of data, and without stream processing there is no big data and no Internet of Things. So people have to now deal with this streaming system. Now let us see about the Spark ecosystem. In the Spark ecosystem you have to now see that there is a Spark core engine, and over the Spark core engine there are different libraries for different type of application, and one such application is called Spark streaming for streaming data analytics, and this is also called the fast data processing. So this particular Spark streaming enables the analytical and interactive applications for the live streaming data. Now this particular platform, which is provided by the Spark ecosystem, is integrated over the Spark core. So the Spark streaming, that is the streaming data analytics, you can apply the machine learning library which is also supported in the Spark core over this Spark streaming, and therefore you can gain insight by applying the machine learning libraries which are built on top of that Spark. Sometimes using this particular Spark streaming and the GraphX, you can construct a graph computation engine and combine the data parallel and the graph parallel operations. Similarly, the Spark streaming also can be converted or can be put into that format called Spark SQL, and it can be used for the structured data and various queries thereafter. So the core engine for the entire Spark framework provides the utilities and architecture for different components. So let us go in more detail about this component, which is called the Spark streaming supported over the Spark core engine. So this particular Spark streaming, this extends the Spark for doing the big data stream processing. So this particular Spark streaming project started in 2012 with a alpha released in spring 2017 with Spark 0.7. Moving out of this alpha, Spark 0.9 is now used. So the Spark streaming has a support for built-in, and they will consume from Kafka, Flume, Twitter and other socket for data ingestion into the system. So Spark 2.x a separate technology based on the data sets called structured streaming. So that has a higher level of interface and is also provided to support the streaming. Now the framework for the large scale stream processing now requires to scale to 100 of nodes and achieve a second scale latency, and has to integrate with the Spark's batch and interactive processing, provide a simple batch like API for implementation of the complex algorithms, and can absorb the live data streams from Kafka, Flume, Zero, MQ and so on. So let us see about the Spark streaming. So Spark streaming technologies will receive the data stream from the input source. So that is what is shown over here, process them in the cluster, that is called the Spark streaming, which is running under the Spark core, and Spark core runs on the cluster. Push out to the database here, that is all shown. So therefore it supports scalable, fault tolerant and second scale latencies, that is the requirements we have seen set for stream processing. So therefore Spark streaming engine will now support the data ingestion from different sources, Kafka, Flume, SDFS, Kinesis and Twitter. Now this will be processed in the Spark streaming, and then it will be stored either in SDFS database or a dashboard. So many big data applications need to process the large data streams in the real time. for example the IoT applications. So sometimes it is also used for website monitoring, fraud detection and ad monetization, which is happening on the fly. So many important applications that process large streams of live data and provides the results in a near real time. So when we say near real time is that means the data comes in the batches and the processing takes a little delay, but it is almost real time. For example, social network trend, website statistics, intrusion detection system, and they require large clusters to handle the workloads and require latencies of the few seconds in this particular example. So let us see why Spark streaming. So we can use the Spark streaming to stream the real time data from various sources like Twitter, stock market, geographical systems and some IoT data and IoT, and perform the powerful analytics to help the business. So Spark streaming, you know, that is used to stream the real time data from various sources, where IoT is one of that source, and it will perform the powerful analytics to help the business by gaining the insight from that particular data into the system. So there is a need for the framework for this kind of analytics, that is the big data or stream processing that can scale to hundreds of the nodes, achieve second latencies and efficiently recover from, and it has to integrate with the batch and interactive processing. So let us see the Spark streaming features. It is scaling is easy to scale, speed, it achieves low latency, fault tolerance, integration and business analytics. So all these are the features of Spark streaming. Now let us consider the stream processing versus the batch processing. So batch processing is the ability to process the data, analyze the data at the rest, that is the data is stored in the databases and it will be retrieve the data from the database. So the data is first stored in the database and then it will be analyzed at a later point of time, and this is called the stored data processing or a batch data processing. So this batch data processing is request based, data is available or at the rest into the database or in the storage system, and whenever the request comes, bulk evaluation is to be performed on the stored data, and this particular type of processing called a batch processing is a short lived processing on demand or a request base. Now this batch processing enables for retrospective, reactive and on demand analytics. Now other type of processing is called the stream processing. So stream processing is the ability to ingest, process and analyze the data in motion or in the real or near real time. So that is called the stream processing. So events or the micro batch driven continuous evaluation and long lived processing. So stream processing is the enabler for real time prospective, proactive and predictive analytics for the next best action. Therefore if you combine this stream processing and batch processing together, then it will become the all data analytics. Now let us see that how you can integrate your stream processing with the batch processing. So many environments require the processing the same data in live streaming as well as in the batch post processing. So existing framework cannot do both and therefore requires a new kind of modern applications. So let us see, there are two ways of doing the analytics. One is that the traditional way of doing analytics is structured and repeatable structure built to store the data, that is you should having the question or the queries which need to be performed on the data. So therefore the hypothesis will pose the number of questions, and based on these questions the entire analytics pipeline is designed. So you have to start with the hypothesis, then you have to test against the selected data and analyze after the landing. So this kind of technique is called traditional analytics, whereas the next generation analytics starts with the iterative and exploratory data, that is the structure. So the data is now processed and a correlation or a linear regression is established out of that particular pattern or data, and then using this particular model later on this particular lot of explore all the data and identity correlation and analyze the data in the motion. That is the next generation analytics which we will talk about. Now existing streaming systems are Storm and Trident. So these follow different kind of semantics. So at least one semantics is used in the Storm. So processes each record at least once, and Trident use the transaction to update the status and the processes, and each record exactly once. So both of them have a different kind of ways. So how does Spark streaming work? So let us see that you have to run the streaming computation as a series of very small and deterministic batch jobs. So live stream jobs will come into the system. For that it divides the batches of x seconds, and this particular live stream is divided into x seconds, and Spark treats these each batch of data as RDDs and process them using RDDs. So RDDs full form is resilient distributed data. So this is the unit of processing into the Spark core engine. So Spark treats each batch of the data as RDDs and process them using RDD operation. Finally the process result of RDDs are returned in the batches. So you can see that this is the live stream. Live stream is divided into the batches of x seconds, and each particular batch of x second is called an RDD at the rate, let us say 1 time unit. This is RDD at the rate 2 time unit, and so on. So these particular batches of RDDs, which is the batches of x second, is given to the Spark streaming for doing this computation. Now Spark streaming in turn this gives these batches called RDDs to the Spark, and they will process the result and give it back the results in this manner. So run the stream processing as the series of very small deterministic batch jobs. So batch sizes are half a second, latency is about 1 second, and potential for combining the batch and the stream processing is possible in this platform. So let us see how you can do the word count with the Kafka. So you can see this Kafka will ingest take the data and perform this word count program in this particular case using map and reduce by the key. So let us see any Spark application. It starts with the Spark driver. These tasks are sent for processing this particular data through the Spark execution. So the user code will run in the driver process. So Spark streaming application, this example shows how to receive the data. So data will be received by the driver. Driver runs the receiver as long as it is running the task through the executor will receive the data stream, and it will divide the data blocks and give it to the other executors to execute in this manner and keep it into the memory after the execution. So this is the processing. Once the executor completes the processing, the results are given to the database and it will be stored in these particular batches. So Spark streaming architecture is the following. So it is called the micro batch architecture, where the receiver will receive the batch blocks, and these batch blocks are given to the executors, that is different servers, and these different servers will do the computation, and that is shown over here. So this particular micro batch architecture operates in the interval of time. New batches are created at regular time intervals, divides the time batch into the blocks for parallelism. Each batch is a graph that translates into multiple job and has ability to create large size batch window as it processes over the time. Now Spark streaming workflow. Spark streaming workflow has 4 high level stages. The first is to stream the data from various sources. These particular sources can be streaming data sources like Akka, Kafka, Flume, AWS, and so on. The second type of source includes HBase, MySQL, and so on. Once this happens, Spark can be used to perform machine learning on the data through the machine learning MLlib API. Further, Spark SQL is used to perform further operations on this particular data. Finally, streaming output can be stored into the various data storage system like HBase, Cassandra, and so on. So this is the typical overview which we have given you about the Spark streaming processing. So here you can see that once the data is ingested out of this Kafka and then through the Spark streaming, what you can perform is the machine learning using MLlib or with using the Spark SQL, you can convert into the data frame and then use it to the further level. So, Spark streaming workflow, if you see that data from variety of sources to the various storage systems, it will be transformed. So, Kafka, Flume, they will ingest the data and put for the Spark streaming, and finally the result will be put in the different storage system like HDFS, databases, dashboard and so on. So, here in this particular figure it is shown that incoming stream of the data is divided into the batches, and that will be done by the Spark streaming, and the batches of input data will be processed by the Spark engine, and the batches of the processed data will be put as the result. So, this particular processing which is shown over here is further detail is given. So, you can see that discretized stream is the proper data structure which is used. So, these are the batches are called D streams, and D streams are nothing but the micro batch RDDs, which are for a particular time interval, they are being chopped off or being divided into that batches of different times. So, data at different timings is being broken up by Spark streaming and give to the Spark engine for doing the computation. Now, once these D stream is given to the Spark engine, then different commands and the operations will be applied. For example, flat map here in this example, a line in a particular document is now divided or is applied using a flat map operation, and from the line it will divide into the words, and the words are being extracted from the input streams between this. So, this is how the Twitter data analytics can be performed. So, you can see that in the tweets Twitter stream will be nothing but in the form of D stream, that is sequence of RDDs representing the stream of the data, and this will be handled with the help of Twitter API. Now, this particular Twitter API will give the micro batches of different time intervals, and they are called tweet D streams. Tweet D streams are stored in the memory in memory as an RDD, that is immutable distributed data types. Now, then on this particular micro batches, the operations like flat map will be applied. So, flat map will be a transformation, will modify the data in one D stream to create another D stream. So, this particular transformation will happen using this new D stream, it will create using flat map. So, new RDDs will be created for every batch. So, this is how the stream processing will takes place. So, the output of this particular transformation will be pushed to the external storage, and so that is what is shown over here, and that will be stored either on SDFS or in any other database. Now, this particular use case, so this particular Spark streaming programming can be either done in Scala or in the Java. So, you can see that flat map and saving into the file, there are 3 lines of code written in the Scala. Similarly, you can write in the Java also. So, let us see about the other aspect, that is the fault tolerance aspect. So, RDDs remember the sequence of operation that it created it from the original fault tolerant input data. So, these input data is now replicated in the memory like this, and when the flat map is applied and if any data is lost, then you know that replication will be used to process this. So, the batch of input data is replicated in the memory of the multiple worker node, therefore, it is fault tolerant. So, data lost due to the worker failure can be recomputed from the input data. So, these principles are already well established in the Spark core, same is used for the fault tolerance. So, let us see the key concepts which we have quickly used up. Let us review that. So, D stream is a sequence of RDDs representing the stream of data such as Twitter, Kafka, SDFS, Flume and so on. Transformation is to modify the data from D stream to another standard RDD functions and stateful functions such as windows and count by value and a window. Output operations is to send the data to the external entity such that SDFS. Another example is to count the hashtags. So, this particular example is shown that hashtags are counted by the value. So, here after the flat map another operation is to be performed, the map and reduced by the key, which will be doing that particular count operation, that is reduced by key. So, third operation is to count the hashtag over the last 10 minutes. So, you can see that here will for this kind of operation you require a sliding window. So, you can see that you have to create a sliding window of 1 minute time. So, this is the 1 minute time, 1 minute interval of a sliding window, and that particular window will now shift after every 5 seconds. So, this is called sliding window, and it now this particular hashtag count the hashtag will be performed inside this particular window of 1 minute time. So, sliding window, you know that it is window operation, window length and sliding interval, that I have already explained. So, after 5 seconds it will shift to another, shift to the right in this manner over the data. So, therefore, if you see this kind of complete details, so this is the hashtag using the sliding window of 10 minutes, it can have 1, 2, 3, 4 different micro batch RDDs, and after 1 second it has to shift. So, it will count over the data in that sliding window, and this will be performed an action, and after 1 second you know that it will be now shifting its values. So, smart window based reduce operation is being supported here in Spark streaming, and also will be arbitrary stateful computation is also supported here, which is nothing but update state by the key. So, arbitrary combination of batch and stream computation is shown here in this particular example. The join incoming tweet with the spam SDFS file to filter for this is you know that it will be joined here with the tweet data, that is the stream data. So, Spark streaming, D streams and batch and RDDs are the different data type or data structures of a Spark streaming is being followed here in this Spark streaming. So, input streaming, after going through Spark streaming it will divide into the different micro batches, and these are all RDDs of different time duration, and they have to be processed by the Spark engine in the batch. So, these particular it will repeat for each batch, and because we are dealing with the Spark streaming data, the streaming has the ability to remember the previous RDDs to some extent. So, D streams plus RDDs will become the power of computation for doing the analytics, and you can see that from D stream to the Spark jobs you can create the for each interval RDD graph is computed for D stream graph. So, this is called a D stream graph, and this D stream graph will contain all the operations which are to be performed on the micro batch RDDs, and the output operation a Spark action is created based on these particular RDDs. So, input source are that out of the box the input sources which are being supported here in Spark streaming is Kafka, SDFS, Flume, Akka, actors, raw TCP sockets. So, input streams, input sources, it is very easy to write a receiver for your own data source, also generate your own RDDs from the Spark and push them in the stream. So, the current Spark streaming input output, you can see that it is supporting various input sources like Kafka, Flume, Twitter, 0, MQ and MQTT and so on, and the basic sources are the socket, files, Akka, actors and so on. Output operations are also supported over here. So, Dstream classes are different, that is different classes for different languages are being supported, Scala, Java, and Dstream has 36 different values, and multiple type of Dstreams are supported through and separate Python API is there. Now, Dstream Spark streaming operations are listed over here. So, all the Spark RDD operations are applicable, some available through the transform operation, for example map, flat map, count, join, that we have already seen. Spark streaming window operations, so window count by window, reduce by window, all these operations are there. Spark output operations are such that print and so on, save as a file. So, fault tolerance, you can see here in this particular slide, the batches of input data are replicated in memory for fault tolerance. So, data lost due to the worker failure can be recomputed from the replicated data. So, all the transformations therefore are fault tolerant and exactly once transformations. So, fault tolerance means received data is replicated among multiple Spark execution, default factor is 2. So, it must protect the driver program, and if the driver node running the Spark fails, then the driver must be restarted on another node requires the checkpointing directory in the Spark context. So, checkpointing saves the data, save the state on a regular basis, that is typically every 5 to 10 batches of the data. A failure would have to replay 5 to 10 previous batches to recreate. The RDDs and checkpoints is done to SDFS or equivalent streaming back pressure is enabled. So, performance, if you see, it can process up to 6 million records per second, that is 6 GB per second on 100 nodes at the sub second latency, that is shown here in this particular graph, and comparing with the other systems is also shown that Spark is streaming, that is 670K records per second per node is there, compared to the Storm, it is able to do only 115K records per second per node, and commercial systems often requires 100 to 500K records per second per node. Fast fault recovery, recover from the faults and stragglers within 1 second, that is shown here in this performance matrix. So, real time applications, let us say that mobile millennium project. So, traffic transit time estimation using online machine learning on a GPS observation. So, you can see here this particular nodes in the cluster, which is also scalable and even very compute intensive, CPU intensive, also requires the machine, and it scales linearly with the cluster size. So, vision 1 stack to rule them. So, you can see that the Spark streaming supports also the ad hoc queries and also with the help of integration with the batch processing. So, Spark program versus Spark streaming program. So, Spark streaming on the Twitter data stream is shown over here, and it applies the Spark streaming function like flat map and on a Twitter log. So, advantage of unified stack here is to explore the data interactively to identify the problem, and same code with the Spark for processing the large logs, and use the similar code in the Spark streaming for the real time processing. So, the roadmap is that we have already covered that Spark 0.8.1 marked alpha, and it is being stable, and a master fault tolerance is manual recovery is enabled. Now, let us see the sliding window analytics. So, Spark streaming windowing capabilities are one of the most powerful way of performing the real time analytics or a stream analytics. So, for that it requires the 2 parameters. One is the window length, that is the duration of the window. So, here you can see that this is the duration of the window, and then the sliding interval, that is after what interval it has to move to the right over the stream data, that window operation. Both the parameter must be in the multiple of batch intervals. So, a window creates a new D stream with a larger batch size. So, here you can see that the original stream of the data is divided into the micro batches, time 1, time 2, time 3, time 5, and over which you have to now define your window operations, windowing capabilities. So, it is windowed D stream, now you start getting as far as the operation which you performed at time 3, and then this particular time interval will shift it, and you will get the next particular result after this. This is called windowed D streams. So, Spark window functions for data frames and SQL is introduced in Spark 1.4. Spark window operations improved the expressiveness of Spark data frame and Spark SQL. So, with the window functions you can easily calculate the moving average and cumulative sum or reference a value in the previous row of the table, and the window function allows you to do many common calculations with the data frames without having to resort to RDD mapping. So, there are different functions which are supported in this window functions called aggregate, UDF versus window functions. So, window functions are complementary to the existing data frames. Operation aggregates sum as sum and average and UDF. To review, the aggregate calculates a result and sum or average for each group of the rows, where UDF calculates one result for each row on only the data in that row. So, therefore, in contrast, window functions calculate one result for each row based on the windows of the row. So, in the moving average, you calculate each row the average of the rows surrounding the current row. This can be done using the window function. So, let us dive into the moving average example. In this example, the data set, there are two different customers who have spent different amounts of money each day. So, building the customer data frame, all the examples are written in Scala. So, here you can see that the customers, one is the Alice and the other one is called Bob. So, these two customers have spent different amounts of money each day. So, you can see that Alice is spending 50, 45, 55, Bob is spending 25, 29, 27. So, date and the amount spent is given in the data set. Now, as far as moving average example, you have to create the window, that is window partition by name and the date and the row between -1 and 1. So, in this window the data is partitioned by the customers and each customer data is ordered by the date. So, window frame is then defined starting from -1, that is one row before the current row, and ending at 1, that is one row after the current row, and for total of 3 rows in the sliding window. So, let us see that this particular moving average therefore will create using the data frame by applying the average functions on the sliding window defined in the window specification. So, just see that 3 different users. So, you can see that sliding window operations is being established here with a moving average of Alice 47.5, then 50, then 50, 27, 27 and 28. So, as shown in the above example, two parts to applying the window functions: specify the window functions such as the average in the example and specify the window specifications. For in the example, you can find out all these details in further examples. So, cumulative sum is another statistics which you can, or another function you can perform in the sliding window over the same data set. So, cumulative you can see that it will take data 50 and the next data when it comes, it will do the cumulative sum, and finally when 55 is added, then it will add. And for the next user when 25 is the amount which is spent, which this is the only, and when the next chunk it will be cumulative addition is done, and finally all that details are given over here. So, in the next example you see that the amount is spent by the customer in their previous visit is automatically previous amount is spent. So, with the 50 previous is not there, then it will be null, and for every data you see that previous values are given. So, these are some of the operations which are there, and then you can also do a ranking. In this example we want to show that the order of customers visit, whether it is first, second or third, the rank function returns what you want over the window specifications. So, you rank this particular way in which the data is coming. So, let us see about the Twitter sentiment analysis using Spark streaming. So, Twitter sentiment analysis is to do a trending topic, can be used to create the campaign and attract the larger audience. So, sentiment analytics helps in crisis management and so on. Sentiments refers to the emotion behind the social media mentioned online, and sentiment analysis is categorizing the tweets related to a particular topic, performing data mining and so on. So, it can be done with this particular. So, to design the Twitter sentiment analysis, where you populate the real time sentiments for the crisis management and service adjustment and for the target marketing. So, sentiment analysis is used to predict the success of a movie, predict the political campaign success and so on. So, to do this let us build the environment and then Twitter token authorization, and then Dstream transformation is being carried out, and this is the result of this particular sentiment for the Trump, which is shown over here. And applying the sentiment analysis, as we have seen from the sentiment analysis demonstration, that we can extract the sentiments of a particular topic. For example, it is a Trump. Similarly, the sentiment analytics can be used for the crisis management and so on. So, companies using the Spark streaming for sentiment analysis have applied the same approach to the following: enhancing the customer experience, gaining the competitive advantage, gaining the business intelligence, revitalizing a losing brand. So, let us conclude this particular lecture here. So, we have seen the stream processing framework, which is for hot data analytics, hot data path analytics, which is also called as a real time analytics or the streaming analytics. It is also called the fast data processing. So, stream processing frameworks like Spark streaming we have seen, an important way of doing this streaming analytics, that is called windowing based methods we have seen. What we have seen is that this particular method to do this stream processing within a particular time and need to be scaled. Therefore, there is a proper framework which is required to do this kind of stream processing, which is scalable to a large number of clusters. We have also seen that the methods, that is in the form of a scale, we have seen that it can achieve seconds scale latencies and also has a simple programming model such as Scala and Java we have seen. Also, we have seen how to integrate with the batch and the interactive workloads for better insight when doing this particular real time analytics. It also ensures efficient fault tolerance in a stateful computation. Thank you.